welcome to The Explainer. So today we're diving into a question that honestly, it kind of shakes up how we think about science itself. It's a journey that goes all the way from atoms to life, and our guide, well, it's a surprising one. Chemistry. You've heard this before, right? That biology is just applied chemistry, and chemistry, well, that's just applied physics. It's this really compelling idea that you can boil everything down, all of reality, to just the behavior of tiny little elementary particles. But what if that neat, tidy story is missing a massive piece of the puzzle? So there's a name for this idea. It's called reductionism. And, for the better part of a century, this has been the main story. The belief was that if we could just figure out the most fundamental, rock-bottom level of reality, then everything else, molecules, cells, life itself, would just sort of fall into place. All right, so let's dig into this traditional viewpoint. It paints a really clean picture of the world, one that people often call the layer cake theory of science. And here's what that layer cake looks like. You've got these distinct levels of reality, just stacked neatly on top of each other. At the very top, you have complex social groups, which are made of organisms. And those organisms, they're made of cells, which are made of molecules, then atoms, and then all the way down at the very bottom, you've got elementary particles. The core idea here is that the rules of any one layer can just be figured out from the rules of the layer right below it. Simple, right?
And wow, this quote from Nobel laureate Steven Weinberg, it just perfectly captures that reductionist dream. He argued that if you keep asking why in any part of science, the arrows of explanation all seem to point down, 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 converging on a single source, the fundamental laws of physics. It's a really powerful vision of a totally unified science.
But, and this is a big but, not everyone buys it. In fact, another Nobel-winning physicist, Philip Anderson, came along and basically threw a wrench in the whole machine with a simple but profound idea. More is different.
Anderson's point was this. As you go up that layer cake, as things get more complex, you don't just get more of the same stuff. No, you get entirely new things. New phenomena, new rules, new behaviors that you literally could not have predicted just by looking at the lower levels. Every single new level requires its own whole new conceptual structure.
And this is where chemistry enters the chat. Chemistry is often seen as this in-between science, but it actually holds the secret key to understanding this whole anti-reductionist idea. And that key is the molecule. Okay, look at this. This shows two totally different ways of seeing the exact same thing. From a physics point of view, methane is just a collection of atomic nuclei and electrons sitting at certain points in space. That's it. But to a chemist, it's a molecule of methane. It's a named individual. It has a unique structure, its own distinct properties. It's got a personality, you could almost say. And that is the huge conceptual leap that challenges reductionism. See, a molecule isn't just a pile of atoms, it's a system. The organization itself creates a brand new reality. It creates a whole that actually changes the relationships between the parts. So this systems thinking, which really comes out of the way chemists see the world, gives us a whole new way of looking at everything. It's got 3 rules for understanding how complexity works, and they might not be what you think.
First up, rule number 1. The whole is more than the sum of its parts. We call this emergence. When individual parts get organized into a system, brand new properties pop into existence that the parts never ever had on their own. Think about things like stability or even life itself. These aren't properties of atoms. They are emergent properties of a complex, organized system.
But here's the twist. Rule number 2. The whole is also less than the sum of its parts. This is the idea of constraint. For an atom to join a molecule, it has to give something up. It loses some of its freedom. It's constrained by the very system it's now a part of. So yeah, organization creates new possibilities, but it also means setting new limits. And when you put those two ideas together, you get the most mind-bending rule of all. The parts themselves are fundamentally transformed by being in the system. An atom inside a molecule is just not the same thing as an atom floating around by itself. Its very nature has been changed. The parts build the whole, but then the whole reaches back and redefines the parts. This creates this really cool effect called circular causality. It's not a simple one-way street where A causes B. It's more like a feedback loop. Think of a thermostat in your house. The room temperature, the effect, loops back to tell the furnace, the cause, to turn on or off. The system's own organization keeps it stable. This is how complex systems, from molecules all the way up to living cells, actually hold themselves together.
So why is chemistry the perfect field to show us these rules? Well, its whole approach gives us this powerful template for understanding complexity, because it does something unique. It perfectly balances the study of stable things with the study of constant change.
Think about it like this. Physics, for the most part, focuses on process, on the laws of transformation and change. Biology, on the other hand, tends to focus on the entity, the organism, the species, the stable thing. But chemistry lives right there in the middle. It gives equal importance to both the stable things, like the millions of named molecules, and the dynamic processes, the reactions that create and change them. It's perfectly balanced.
So when you put it all together, you see chemistry's really special and powerful role. It's the bridge between the non-living and the living world. It's a science that doesn't shy away from richness and detail. I mean, it gives individual names to millions of different things. And because of this balanced, systemic view, the chemical way of thinking becomes this incredible model for any field that's trying to get a handle on complexity, whether it's economics or ecology or sociology.
And that kind of leaves us with one last big thought to chew on. For so long, we've been taught to chase after a single, simple theory of everything. But what if chemistry's secret philosophy has been pointing to the truth all along? What if the real beauty of our universe isn't found in some ultimate, bottom-level simplicity, but in the rich, endless, and emergent complexity that blossoms at every single new level of organization?